Right. So, in our course selected topics in decision modeling, we are in our 38th lecture, that is on particle swarm optimization technique. Now, particle swarm optimization is a nature inspired evolutionary and stochastic optimization technique to solve computationally hard or difficult optimization problems. PSO, as in short we call particle swarm optimization, is a robust method for optimization based on movement and intelligence of swarms. Now, what is that robust? Robust usually means, that means the method works in in many different conditions. It really solves problems in all different situations. It was developed by James Kennedy and Russ Eberhardt in 1995 and has been successfully applied in a wide range of search and optimization problems. Now, it really abstracts the working mechanism of swarms, like swarms of birds, fish, etc. What really happens in this method? We take a set of particles, right. So, supposing we have a solutions space. So, within that solution space, we take several particles and each particle actually represents a particular solution, right. And let us say each particle is searching for the optimum solution, and finally therefore, when all the particles finally come to certain points around the best possible solution, then slowly we see that the iterations really try to reach to the best possible solutions. The question is how it actually happens. How it happens that each particle is continually updating its position according to its previous experience and the experience of its neighbors. That means, a given particle, see that is what the birds and fishes actually do when they move in a swarm. Not only each bird is trying to move based on what that particular bird thinks is the best direction, but also what the group thinks as the best direction. So, it takes feedback from both the global best and both the local best. So, it is a combination of search for the local best and the search for the global best. Now, there are three vectors. The first, each particle is composed of three vectors, the x vector, the p vector and the v vector. The x vector records the current position of the particle in the search space. The p vector records the location of the best solution found so far by the particle, and the v vector contains a gradient for which particle will travel if undisturbed. So, that means for every particle we have a velocity vector, a position vector, right, and the p best, that means the best possible solution. So, there is a particle position and the best possible solution that this particular particle is trying to reach out of these. So, that is also recorded. So, how exactly it happens we shall see through an example, and all these vectors are continually upgraded, is all right. So, the positions, the velocity, the best possible solutions, the global best and the local best, they are all continually updated. So, see, try to understand. Suppose this is our solution space, and supposing I have my 5 different particles, say P1, P2, P3, P4 and P5. Now, look here. So, each particle is having a velocity and it is trying to move in search of a certain solutions. So, what are those solutions? One is, for each particle there is a local based and there is a global based. So, you see this is the global based. To the global based, every solution is trying to move, but individual particles, they are trying to move also to a set of local based. So, you see these are all local based and this one is the global based. So, each particle is having a velocity from its current position, trying to move to a combination of the local based and the global based solutions. So, what happens after some time, you may find the particles have narrowed their gaps, right. They have narrowed their gaps and they are very near to the global based solution, is all right. So, this is the essential idea of the particle swarm optimization. We have a number of particles which covers the entire solution space. Each solution is trying to move in a certain way, so that it tries to reach the global based for the entire group and the local based for its own. So, that finally, it tries to get to the best possible solution as quickly as possible, right. So, PSO and GA, while GA has genetic algorithm has selection operator, PSO does not have. So, there is no selection operator in PSO. PSO does not implement the survival of the fittest, right. There is no selection, crossover, etc. All individuals are kept as members of the population throughout the operation of the PSO. So, each individual is available, but obviously those individuals as they move, they are actually going to a new solution. That is what is happening in PSO. So, this is the framework or the schema for the PSO algorithm, that is, we start initialized swarm with a random position x 0 and a velocity vector v 0. Then for each particle evaluate fitness, is all right. Then if fitness is better than the G best, then we update the G best. If the fitness is better than the P best, then the P best is updated. That means, you keep updating the global best and the particle best. So, P best and G best, they are updated, and if the terminate is true, then G best is output and stop. Otherwise, go to the update velocity, this is the iteration update velocity. So, you see how the velocity is updated, it is updated by C1 W into Vt. So, W is inertial weight which is with regard to its velocity, C1 is and C2 they are acceleration coefficients. So, C1 into a random number and P best minus xt, xt is the current position, and C2 into another random number and G best minus xt. So, this is the gap from the particle best, this is the gap from the global best multiplied by a random number and a coefficient. That is how the velocity is updated. Now, once the velocity is updated, if you add the current position to that velocity, then we get the new position. So, then we have the next particle. So, basically this is done for each of the particles. So, each of the 5 particles, if 5 particles are taken, this is done, and then after that we see that what is the situation, and we go for the next iteration, right. So, I hope you understood what is really happening, that in the solution space we initially find a certain number of particles. Suppose number of particles should be quite large. For small problems we may take only few particles. For a small problem, let us suppose we have taken 5 particles, then for each particle we keep calculating the velocity, as initially we have to do all those initialization, and after that we have to check against the fitness and g based and p based values, and then update velocity by this kind of formula and keep iterating. Now, the basic concept of PSO lies in accelerating each particles towards the best position found by it so far, that is p best, and the global best position obtained so far by any particle with a random weighted acceleration at each step, right. And this is done by simply adding the v vector and x vector to get another x vector, right. Once the particle computes the new xi, it is then evaluates the new location and the p best and the g best and p fitness and all that. So, I think an example will be very clear for you. So, look here, this is an interesting diagram. So, this is the particle's current position. So, see, look here. So, this is the particle's current position. So, one particle's current position is this. Now, this is the best possible solution obtained so far, and this is the global best solution obtained so far. So, the particle has got 3 components of movement. One is towards its velocity direction, another is towards the p best, another is towards the g best, right. So, the gap of this position from p best and g best multiplied by some random numbers and 2 coefficients and also an inertial coefficient w for the velocity gives the next velocity thing. Here velocity is more like a position change. So, whatever we have, the current position plus velocity will be the new position, is all right. So, that is what we are calling psychosocial compromise, fine. So, that is what it is. Now, once we have this, then our next calculation, you can see here that is what is being happening. So, particles current position, see, just see this particles current position. So, it moves that I proximity and g proximity between p best and g best. So, particles best position so far and global best position attained. So, the movement of the particles will be something towards v, something towards p best, something towards g best, is all right. So, it is really a balance between diversity and towards a better fitness, is all right. So, when you have a number of particles and each particle is moving to its own best and to the global best, it actually ensures that the population diversity, that means the entire solution space is covered in an adequate manner, is all right. So, that is the essential idea of the PSO technique, right. So, that is where it finally moves. So, some of the initial parameters: swarm size, position of particle, velocity of particle, maximum number of iterations, and control parameters: swarm size, inertial weight, acceleration coefficient C1 and C2, and the number of iterations, all right. So, this is, look here, the inertial weight. A large inertial weight facilitates a global surge, while a small inertial weight facilitates a local surge, is all right. So, should be careful on that, that inertial weight, if we take large, then this helps in global surge, small it helps a local surge. Similarly, the acceleration coefficient C1 larger than C2, greater global surge ability, C2 larger than C1, greater local surge ability, fine. So, let us now look at a numerical example. So, this numerical example is like this. So, first of all, objective function is maximize f x equal to 1 plus 2 x minus x square. So, it is a simple problem that we have to maximize this function for the value of x and try to see how we try to obtain this by the PSO technique. So, we decide that we take the w equal to 0.7, that is the weight for the velocity, C1 and C2 the coefficients for global and local 0.2 and 0.6 and 5 swarm particles we take, and for simplicity's sake we take only 4 iterations. Then we need certain random numbers for updating velocity. So, you see, whenever we talk about random numbers or any number, the position, we are going to write a matrix of size 5. Why matrix of size 5? The essential idea is that there are 5 particles. So, each particle is for, each number is for a particular particle. So, for example, for the first particle, the 2 random numbers are 0.4657 and 0.5319. So, we decided to keep the random number fixed for the iterations, different iterations. In reality, we may take different random numbers in different iterations, is all right. So, maybe one can take these random numbers for iteration 1, in second iteration it can take another set of random numbers, but we have decided to keep them fixed. So, the problem is clear, we are maximizing f x equal to 1 plus 2 x minus x square. We have taken such control parameters, we have taken some random numbers, right. So, now the first thing is we initialize the fitness of all particles to zeros, that means initial fitness let us take as zeros. Now, the current position that random numbers can be used. So, what we do, the current position of these at the 0th iteration can be taken as 10 times R1 minus 0.5. So, this is our R1. So, minus 0.5 into 10, then this is how we have found out the current position of the particles, all right. So, you see, multiplied by 10 to initialize at least some particles to be greater than 1 and subtracted 0.5 to generate both positive and negative positions, right. So, we have to ensure that these sort of things are to be done, plus another thing should be kept in mind. So, look at the function. So, you see, the positions should be such that they cover our solution space, is all right. So, the initial positions, basically these particle positions actually represent the functional, the x value, is it not. So, this is a function of x. So, these particle positions actually represent the x value. So, the x values should be such so that it covers the available solution space in an appropriate manner. It should not be that the solution space is not properly covered. So, it should be ensured that is what is done here by multiplied by 10 and then divide minus 0.5 to generate both positive and negative positions, right. So, similarly, the velocity is computed by using R2. R2 we already defined initially. So, if I in this case minus 0.5, then we obtain the velocities. So, obviously, different problems, different kind of solution space and different ways we should be redefining our the velocities and positions, so that it covers the entire solution space and the velocity should not be too low or should not be too high. So, those kind of fine tuning has to be carried out while initializing the velocity and initializing the positions. So, good. So, what we have done? We have obtained the current positions of the particles and we have obtained the current velocity of the positions of those particles. So, now what we see, already we got the current positions. So, look here, this is our current positions Cp0. So, this is our current positions are already obtained and current velocity is already obtained. So, from the positions, if we do the functional value, because you remember that our function x f x equal to 1 plus 2 x minus x square. So, that was the function. So, if we put the position and put that, we get what is known as the fitness value. So, Cp1 square is obtained by squaring individual elements of Cp1. So, here Cp1 is like x, is not. The current positions of the particle are like the x values. So, if we put the function, then we get the current fitness. So, what have we done? We have obtained the, for the first iteration, we have obtained the current position, which is as same as Cp0 we have taken. We have taken the current velocity, that is V1 equal to V0. So, already that is obtained, and making use of them we have obtained the current fitness, right. So, what are the things that we have calculated for iteration 1? We have obtained the current positions, we have obtained the current velocity, and we have obtained the current fitness, right. So, these are the 3 things that we have obtained. Current positions is taken same as iteration 0, current velocity taken same as iteration 0, current fitness we have found by putting in the original function f x. So, x is known and f x was 1 plus 2 x minus x square. So, instead of x we put the Cp positions. So, like Cp1 is 0.0319. So, when you put 0.0319 we got 0.1976, when you put 0.3185 we got this, like this we obtained the current fitness values, right. So, we obtained this current fitness. Now, the question is which one is the best local best positions? Look here, the local best position are nothing but its current position, because we do not have anything else. So, we have to assume whatever is the current position, that is also the local best position at the iteration 1. So, our Cp1 was these values. So, same values are going to be our local best positions. And what are our local best fitness? Again it should be current fitness, because we do not have any other thing. So, this is going to be our current fitness values. Now, what are the best possible values? Look here, you remember the problem was one of maximization. So, out of these different fitness values, the best one is nothing but 1 point, see look at these numbers, 1.0755 is the best. So, we call it our global best. So, global best is 1.0755 for the fifth particle. So, that is our global best fitness. So, this is the maximum of the local best fitness. And what is the global best position? For which position is this particular value? That was the 0.0385, because for these x, this f x has been obtained. So, that means global best position will be 0.0385. So, so far nothing very difficult. I hope everyone has understood that what exactly we have done. We have obtained the velocity, the current position, the local best positions, the local best fitness, the global best fitness and global best position. That was for the iteration 1. Now, from iteration 1 as we go to iteration 2, now we apply what is known as the velocity, that is psychosocial criteria. So, as I have told before, the new velocity will have a weight to the previous velocity, the current velocity, then the C1 and C2 two coefficients along with two random numbers R1 and R2, then local base position minus current position and global base position minus current position. So, these weight has to be obtained. Now, we have from iteration 1 the V1 values. So, this is our V1 values, and we decided to take these random numbers. So, these are our random numbers. So, for the first particle, so there are 5 particles. So, these are the first particle random numbers. The CP1 for this the position was minus 0.3425, the local best was minus 0.3425 and global best was 0.0385. So, all these things you see they are all there. So, all these values we can make use of. Then V2, that for the first particle the V2 will be then 0.7 into V1, that is the whatever is the 0.0319, 0.2 into R1 LBP1 minus CP1, 0.6 into R2 GBPI minus CPI. So, it comes to 0.1439. So, using all of these for iteration 2, velocities for all the 5 particles can actually be obtained, right. So, we have obtained the velocity for the iteration 2. Now, once we have found iteration 2 velocity, what will be the current position of the next iteration? It will be the old current position plus velocity 2. So, if you add these values, the CP1 values to the V2 values, we get the next current position. So, this is going to be our next current position, which is nothing but a simple addition of the CP1 and V2 terms. And what will be the current fitness? The current fitness could be obtained by putting the functions. So, taking the SM as x, finding the fx values will be the current fitness values. So, what will be the local based fitness? So, look here, LBF1 was these values. So, what will be LBF2? The local based fitness of iteration 2. So, you see 0.5634 and 0.1976, this is better. Then 0.4250, this is better. 0.2860, that is better. 1.28, that is better. But out of these 0.5794 and this is better. So, that will be our LBF2. So, only the 5th position is different. So, then from there we can find out that we know CP2, we can find out LBF2. Now, from there we see the global best and the global best fitness and global best position, right, and also the local best positions can be obtained as well. So, all of these things could be very easily calculated for the different iterations, and all these are tabulated here. So, look here. So, that first of all from V1, so these are the equations that are used, that Vi plus 1 equal to WVi C1 R1 LBPI local best minus Cp, then global best minus Cp, then Cp equal to Cpi plus Vi plus 1, local best fitness maximum of Cfi plus 1 and LBFi, and global best fitness is the maximum of LBF. So, all these calculations are noted here, is all right. Now, on similarly, when you calculate for 2 more rounds, that is the 3rd iteration and the 4th iteration, then we can find out after these 2 iterations, we have found out the global best after 4 iterations as 1.9974, and for the value, the global best position, that is 1.0510, right. So, that is going to be our best position and best fitness obtained after 4 iterations, right. So, it is just calculate the velocity, calculate the current position, calculate the current fitness, from there find out the local best fitness till that iteration, global best fitness, local best position and global best positions, do those calculations. So, all right. So, this is how the summary, that this is the function for which we are trying to find out the final solution. maximize fx 1 plus 2x minus x square, theoretical value is 1. So, this is 1 x 1 and the value is 2, but what we got through our iteration, we got 1.0510 and fx star as 1.9974. So, we got a very near solution by only in 4 iterations. Maybe if we do more, we may be more near to the theoretical value. Is all right. So, this is how the PSO is applied. I am sure you can do more problems of PSO and you will be able to learn it in a much better manner, right. So, thank you very much for patiently hearing.